Hello, everyone. We're going to now talk about the last operation for matrices, transposition, or the transpose of a matrix. So here we go. So we start with a matrix with m rows and m columns, so a m by n. And the transposition is an operation that is always defined. And the transpose of A, the notation for the transpose of A is A to the power of T. So if your matrix is a m by n, so m rows and n columns, the transpose will be a n by m matrix. So the number of rows now are going to be n, the former number of columns, and the number of columns are going to be m, the former number of rows. And here the idea is that the entry on the ith j column of that transpose is the former. So if you're looking at the transpose and you wonder what's on the ith j column, well, it is what it used to be on the jth ith column. So, and this is true for all entries. But the simplest way to think about this operation, because this is a simple operation to compute, you can think about take the first row of A, and this will become the first column of that transpose. And the second row of A will become the second column of the transpose. And all the way to the last row, the mth row of that matrix A, to become the nth column of that matrix A. And actually, you can do it the other way. You could say that the first column of A becomes the first row of A transpose, and etc. So it's up to you. If you're a row person, just take these rows and make them rise as columns. If you're more a column person, well, take these columns and make them lay down for you if you are more romantic type person. All right, let's just do some example. Let's look at an example. I have here a matrix A with 3 rows, and we're going to transpose that matrix going from A to A transpose. So the way I like to do it is I like to take the first row, 1 minus 3, 5, 7, and then it becomes the first column of that matrix A transpose. Then the second row, 2 minus 2, 4 minus 2, will become the second column of the matrix A transpose. And finally, the last row, 3, 5, 7, 9, will become the last column of that matrix A transpose. And that's as simple as it is. Let's do more example. So here now I have 4 matrices, A, B, C, and D. You can highlight the rows or the columns. It does not matter. So I will do these examples in different ways. So I've circled my rows for A, my columns for B. Since C was a row matrix, I decided to circle the row, and D is a 1 by 1. So there's only one thing to do, and it's circle the number. And now let's do our transposition. So for A transpose, the first row becomes the first column. So 1, 2, 3, 4 is now the first column of A transpose. 0 minus 1, 0 minus 1 is now the second column of A transpose. 7 minus 7, 7 minus 7, 7 and minus 7 is the third column. And then the last row, full of zeros, is now the last column of matrix A. But like I said, you can also take those rows and lay them down as column. So the first column of B, 1, 1, 5, can be now the first row of B. And then the second column of B, 3, 4, and 6, is now the second row of B. And then for C, the only row becomes the only column. And for D, well, not much happens. Okay, so the row lays down or the column lays up, nothing is going on. All right, that's it for that example. It's beautiful. I know you like it. And now move on to the last section of this chapter. And this last section is just about special matrices that are alive in the universe of matrices, the zero matrices and the identity matrices, which are basically the zeros and the ones for matrices. Like just like when you do algebra with real numbers, where you have a 0 and you have a 1. For matrices, there's a lot of zeros and there's a lot of ones, and I'll just show you which one is which. So for my matrices below here, I have my definition of my zero matrices. So a matrix filled up with zeros everywhere. So if all the entries are zeros, those are examples of zero matrices. And because matrices have different size, there's actually appropriate notation for those zero matrix. So for example, that first matrix, a 2 by 2, is going to be denoted by 0, 2 by 2. The second one is a 3 by 3, so it's 0, 3 by 3. The second one with 2 rows and 4 columns is 0, 2 by 4. The fourth example is a column matrix, a 5 by 1, so it's 0, 5 by 1. And our last little 0, 1 by 1 is 0, 1 by 1. So we cannot just write 0 because we need to understand what's the format of that matrix. So there's a lot of zeros, and to make sure that we know which 0 we're talking about, we use that subscript to say that, okay, here's a matrix filled up with zeros with a specific dimension. Why do we call these matrices zero matrices? Because they act like zeros. So the next remark is just a bunch of list of properties for those zero matrices, which are exactly the same as the number 0 for a real number. So if you start with a m by n matrix, a regular m by n general matrix, the first property is that if you go a plus the zero matrix m by n, or if you do the zero matrix m by n plus a, guess what? You're getting a again. So just like any number plus 0, any matrix plus the zero matrix of the corresponding size so that the addition is defined is a again. If you go and, so the second property, if you take a minus itself, you're not going to get the number 0, you're going to get the box of numbers filled with zeros everywhere, where that matrix is, with the correct notation, 0 m by n. And if you take the matrix 0 minus a, you're just getting minus a, the matrix minus a, which is the same as multiplying a using scalar multiplication by minus 1. So that's one way to find the negative of a matrix. And then the final property is that if you have a zero matrix of the right size, so for example, because A is a m by n, if you multiply by the square matrix 0 n by n, you're going to get the box back filled with zeros. Just like if you multiply a number by 0, you get 0. If you multiply A by a zero matrix where the multiplication is defined, you're going to get a matrix filled with zeros. So really, the zero matrices are the equivalent in the matrix universe, or the universe of matrices, sorry, of the number 0. The next example is an example that I really like. Of course, I love everything that is linked to mathematics, but I have here 4 2 by 2 matrices, and I'm going to do some special computations with these matrices. I'm going to multiply A and B, multiply A and C, and multiply also A and D, and try to make some sort of funny connection of some weird algebraic phenomenon that appears for matrices that do not appear normally for a real number. For example, and this is good practice for matrix multiplication when you're learning this, so if you practice multiplying A times B, so do it as a nice matrix multiplication, verify that you're getting 3, 4, 6, and 8. And then multiply A and C together, so do your matrix multiplication, and verify that you also get 3, 4, 6, and 8. And this is very strange. Why? Because we have this matrix AB that is such that when you compute the result, is exactly the same as A times C. But those matrices B and C, if you compare the matrix B and the matrix C, they're not equal. So it's like you cannot simplify. You cannot just say, oh, if you have a matrix equation AB equal to AC, you cannot just say I'm canceling on both sides. That doesn't work for matrix multiplication. So we're so used to, if you have, for example, for real numbers, so if you have like an equation where you say, well, xy is equal to xz. If x is not 0, then you know that y is equal to z. So you are allowed to divide by x on both sides. And the only way that xy is equal to xz is if and only if y is equal to z. And here you can see that A is not the zero matrix. I'm not just multiplying 0 by any number and getting 0. I have this really weird property where A is not 0. I multiply A by B, multiply A by C. I get the same matrix, but B and C are not the same. Again, this is just me being like crazy turned on by that stuff, but we're losing that property for matrix multiplication. The next one that is even crazier is if you take A and D. So if you multiply A, so take the matrix A. So again, good practice here. If you're learning matrix multiplication still, those are very nice, cute example, not too difficult to compute. Circle your rows on the left matrix A, circle your columns on the right matrix D, do that matrix multiplication, and wow, what you will get is a bunch of zeros. So why is this so strange? Well, A and D are not zero matrices, but their product is the zero matrix. And this is really a property that is strange because we're so used, again, for real numbers. If I say that I have two numbers, let's say x and y, let me just write it down for you. So if I say, hey, x times y is equal to 0, then you know that one of those two numbers must be equal to 0. So the only way you will land on 0 after doing a multiplication is if and only if one of those two numbers is equal to 0. So what a weird property. You go A times D, you're getting the 0 matrix 0, 2, 2, but those two matrices are not equal to 0. So it's possible in the universe of matrices that two matrices multiplies each other and they land on 0, even if one of them even if both of them are not the zero matrices. Fantastic. So some weird phenomenon. AB equal to AC does not imply that B is equal to C, and AD equal to 0. It does not imply that A or D is the zero matrix. That's basically that remark here that I have in the summary. So for in general, okay, if you have AB equal to AC, it does not imply that B is equal to C. And if you have AB equal to the zero matrix, it does not imply that A or B is equal to 0. Is this really important for you? Probably not, but still a very cute property that I enjoy, especially on a Friday night when I'm alone with my box of wine. All right, let's move to the next definition. We finally reach that last definition of this chapter, the notion of the identity matrix. This identity matrix is going to play a big role later when we're going to talk about the inverse of a matrix and how to compute the inverse of a matrix. So what is the identity matrix, or what are the identity matrix, which will be the equivalent of the number 1 for matrices? So the equivalent for the number 1 for matrices is not simply just a box filled up with ones. So first and foremost, an identity matrix is a square matrix where the only place you see the ones is on the main diagonal, and everywhere else we have a bunch of zeros. So here I have my first three identity matrices that are going to be important. So I have I2, and you can see here for I2, I only have the one on the diagonal. So I2 means I'm dealing with a 2 by 2 matrix. I3 is a 3 by 3 matrix where the ones are only on the diagonal. I4, the ones are only on the diagonal. You can see that above and below all these diagonals, I have a bunch of zeros. So in general, IN is a n by n matrix where you have zeros everywhere except on the diagonal. Remember, the diagonal of a matrix is these are the entries where the row number is equal to the column number. So that's 1, 1, 2, 2, 1, 1, 2, 2, 3, 3, 1, 1, 2, 2, 3, 3, 4, 4. There's no other diagonal for a matrix. And those are the identity matrices. All right, the next example will help us illustrate why these identity matrices are the equivalent of the number one for real number. So in other words, when I'm going to be multiplying matrices by the identity matrices, I'm just going to get that matrix back. So the next example, I have here a matrix A, which is a 2 by 3, so 2 rows and three columns. And I'm going to compute I2 times A, and then I'm going to compute A times I3. Here, notice that I have to use different identity matrices because I want to make sure that the matrix multiplications are defined. So I need I2 first because I want the 2 by 2 multiplying the 2 by 3. So I want to make sure that the inner number match. So the only identity matrix that I can have on the left side is a 2 by 2. Meanwhile, for the right side, if you start with a 2 by 3, the only identity matrix that I can have on the right side is a 3 by 3. Remember, the identity matrices are square matrices. So because I want the inner number to be 3, well, the other number for that matrix needs to be 3 again. And again here, I love those examples because those are nice examples to practice matrix multiplication. So if you start with I2 and you multiply it by A, so verify, do your matrix multiplication, and you will see when you circle the rows of I2 and the columns of A, and after you take all these columns and you make them lay down on the rows of I2, double check that you get 1, 2, minus 3, 0, minus 1, 10, which is exactly, again, the matrix A. So this I2 times A, after you do that matrix multiplication, results with the matrix A again. And then on the other side, it's the exact same thing. So if you start with A, so remember the left matrix is always columns, and then you multiply it by I3, where I circle the columns of I3. If I take all these columns and I do my matrix multiplication, what you're going to get is, again, the matrix A. So that matrix multiplication, and again, do it. It's so fun. Do it. Do that matrix multiplication. A times I3, you're going to get A again. So here, when I multiply I2 times A, I get A. When I multiply A by I3, I get A. So that identity matrix, or those identity matrices, are just like the number one for real numbers. So that's essentially my last remark of that chapter. Just like I just said, if you start with a general matrix and it's m by n, if you multiply the matrix A by in, again here, make sure that you understand that only in fits, because if A in general is a m by n, the only square matrix that works is a n by n. So you can only multiply by the number one that is in on the right side. And if you do im times A, and again here on the right side, there's only one size that fits, so that matrix multiplication is defined. So in both cases, so A times in, boom, I'm getting, hello, boom, I'm getting again A. And if I go im times A, I'm getting A. So those matrix identity matrices are really the analog of the number one. All right, so for this section / chapter, that's it. That's all. Bye-bye.